again, I don't really want to do this. I would prefer to say it's just like translational kinematics, but I get disappointed when I do that. And so let's just see for a moment the level of disappointment I should expect out of you. Now, I don't know why I'm putting that in the video, but why not? Maybe I won't be. Maybe you guys will be better. You are not going to disappoint me. It's going to be awesome. We're going to be excited. I have a wheel here, and the wheel has spokes. I want to put some spokes in the wheel just so it's all spokified. So they're spokey wheels. Kind of there. Good enough. All right. Let's see. I want to do the simplest thing first, and then we'll build up. Let's say the wheel rolls 10 meters along a level road. It rolls 10 meters. And let's say that the radius of the wheel is 0.25 meters. Can you, with all of your advanced knowledge, figure out how many rotations the wheel makes when it rolls 10 meters? And there were some right answers, but whoa, there were also some not. Look, the easiest way to do this is to remember, say, I don't know, grade school. Every one time the wheel rolls, it rolls one circumference, right? So if a circumference is 2 pi r, then if it rolls that far every one rotation, then if it's going to roll 10 meters, that should tell me how many rotations, right? That's one way to do it. So that definitely rules out 20 as the answer. An entire table convinced themselves that it was 20. Groupthink is fun. There's a few people who did 10. That's interesting. 10 meters. I guess that's where the 10 came from. But how about this? We actually learned this already this year. That's what I think this is funny. Because at one point when we were doing centripetal acceleration, I talked about a conversion between angular measures and linear measures. We could do it this way. It's 10 meters. We're looking for delta theta, the number of rotations made. And we know that the radius is 0.25 meters. This would work. The problem with this answer is this answer gives me my value in radians. So this would be 40 radians. And I asked for rotations. So you would have to remember that you would have to convert from radians to rotations. One rotation is 2 pi radians. And this will give you the 6.4 rotations or revolutions of the wheel. So, all of that to try and drum up a reminder of something I actually taught you back in
October.
But it's been a long time since October. Many, many things have happened. I that because I want you to think about something for just a minute, and I hastened to do this, but this is what I did in 6th period, and I think it at least bears a little bit of representation. Does this look familiar to you? Now, we know that there's a whole bunch of those, right? There's 5 of those. But if I just look at this one for just a minute, do you remember then that there's like a set of conversions? There's that one. There's this one. And there's this one. Ways to convert from translational motion to rotational motion. We didn't talk about this one, but we did talk about these two. So I think I bear it out. We brought this one up, but we didn't use it very much. The right side of this is all the angular values. The left side of this is all the linear values. So consider that this relationship could be written in its angular form for an object that is rolling. Right? This is the whole rolling part. So I could write this as omega times r equals alpha times r times t plus omega naught times r. Right? I'm just substituting in using that and that. However, if you look carefully, and I'm sure that you are all looking carefully, you're noticing that by looking carefully, every term has an r in it. Right? Can I just factor out the r and divide it out on both sides as long as it's non-zero? I believe so. So I can say that I'm going to do an extra step because I saw 3 heads that were being shaken, but I will factor out the r from both of these terms. And as long as the r is non-zero, I can cancel it. So I get this is an angular kinematic equation. It describes the angular motion of an object that spins. It doesn't even have to be rolling. A spinning object is going to obey the same kinematics equations as an object that has what we call translational motion. In fact, that's what I do. I want to make sure you understand that there is translational kinematics and rotational kinematics. Both of these are kinematics. The translational ones we know. And although I should write them all out, I think for the sake of time, I'm going to only write out the top 3. I figure if I can do that, you guys can do the rest. Right. These are the ones that are on your equation sheet. We use these a lot. There are 2 others. Look them up. So I already showed that this one is omega equals alpha t plus omega naught. So is it a big stretch to say the next one would be delta theta equals 1/2 alpha t squared plus omega naught times t? Does that make sense? Any question about that? So omega squared minus omega naught squared equals 2 alpha delta theta. Rotational kinematics. They're actually on your equation sheet, these 3. In the middle is how you can go from one to the other. So, I put this here, but this doesn't apply in every circumstance. It applies for things that are rolling. That's a good circumstance. It applies if you have something that has, golly, Mr. Shelton. If you're trying to find out how far an object maybe on the edge of something is moving. Or if you have something that's spinning and you're trying to figure out maybe, what the linear speed of a point on the edge is, you could use these. But it's kind of a go-between. But just remember that on this side, these would have to be in radians in order to be used here. But this also means that we have a whole group of traditional rotational variables. Delta theta, omega naught, omega, alpha, and t. In the same way that we had delta x, v naught, v, a, and t. Now, in both of these, we are assuming something. We are assuming constant acceleration. Like anything else, the rotational characteristics of an object's motion are based on whether it's a constant acceleration or not. Now, we defined these already before, so I don't believe I have to give you names for each of these, do I? So remember, speed, velocity, acceleration, you put the word rotational or angular in front of it, and you've got the other variable. So I will never say rotational displacement. I almost always say angular displacement. But the other ones, I will use rotational or angular interchangeably. Just some reminders, though, that I do want to remind you about. This is going to be radians per second, RPM, or RPS. Those are the units we'll use for angular speed. And angular acceleration, almost always radians per second squared. I never ask for anything else. And for angular displacement, rotations, sometimes called revolutions, or in a very narrow circumstance, radians. So delta theta usually favors rotations or revolutions. Angular speed, RPM, radians per second, rotations per second, those are pretty much even across the board. Angular acceleration is almost always radians per second squared. Now, I believe that was enough in the Ask 6 period. Hey, how about we just try like a little quiz on this tomorrow? And they almost slipped out. So I have time to explore this, but should I want to give a quiz tomorrow, a simple, straightforward, like primer to this would be, imagine this wheel starting from rest and rolling down a 5-meter long ramp. And imagine that by the time it makes it to the end of the ramp, it's traveling, I don't know. Let's say it's traveling 8 meters per second. What was the angular acceleration of the wheel? Yeah. Yes. Now, the bell's going to ring in a second. There is more than one way to do this problem. You could do the whole problem using translational values, because you have 5 meters, 0, and 8 meters per second. So you could find acceleration and convert it to alpha. Or you can convert everything to angular values and use the angular functions. Doesn't matter which way you do this, but look,